And it will speak about large inequalities economies.
All right, thank you. It's good to be here in person. Looking forward to the rest of this conference. Now, I agree with you that I'll be very happy when my talk is over. I can enjoy myself. So let's just jump in. So just to set a little bit of notation, I want F to be a family of automorphic forms. And I want to let lambda f of n be its Dirichlet series coefficients. So given the family, there are a number of things we might be interested in about the family. So one of the most basic questions we could ask about a family is just how big is it? How many elements are in the family? Ramping up the difficulty a little bit, the next thing you might ask is for low-lying zero statistics. So we've seen some discussion of this earlier in the connection with random matrix theory. Next level would be asymptotics or bounds for moments of L functions. And we saw quite a bit of this in Sound's talk earlier. And yeah, so and then arguably a level beyond that would be a large sieve inequality. This is in the sense that if you have a large sieve inequality, that implies certain bounds or bounds on certain moments. Sometimes you can take higher moments that go beyond the large sieve inequality. So I don't want to say one is strictly easier than the other, but in some sense, this is pretty difficult. So what is a large sieve inequality? It's a bound on a certain bilinear form. So you inside the square here, you have some completely arbitrary vector of coefficients, these a sub n's, and you sum this up. So this is sort of like a dot product between your vector and your arithmetical data, your coefficients, and then you look at the sums of squares of these numbers, and we're looking for a bound in terms of we'll call delta, this delta of Fn, and it's normalized by the sums of squares of the coefficients. And so one of the key things in a large sieve inequality is that we're looking for a bound that is holds for completely arbitrary choices of coefficients. And also we would like to prove this for delta as small as possible. So it's pretty easy to prove, like there are trivial bounds that you could prove that you know, are, as the name would imply, pretty useless in practice. But so you have to work harder to get better bounds. So one of the reasons I'm interested in this is that I think this is a good way to tell us something about a family. So if we can, this is just really a way of testing our knowledge about a family and really giving us quantitatively strong information about these coefficients. So one of the most important principles in this theory is the duality principle. So it says that, well, it's just a principle from linear algebra, but in practice, what it does is it means that, so just to, basically you can reverse the roles of the inner sum and the outer sum. So you can, like in the first line, I've got the sum over m on the outside and n on the inside, and then you can reverse the roles of those two. These two norms are equal to each other. So the first norm, so the value of delta for the first norm is the same as the value of delta for the second norm. So the minimal value of delta. So this is true because we're looking for arbitrary coefficients, and it's difficult to sort of convert information from one side to the next. But so this is one of the reasons why it's important to study this for arbitrary coefficients, is because it lets us use the duality principle. Great. Okay, so for this particular, yeah. Oh yeah. Oh, so I'm just scaling it. So maybe you can't see it very well, but that's supposed to be a bold C. That's a vector. That's the vector of the C sub n's. And so that's just the length of the vector. So saying the length of the vector is 1 is same as saying the length squared of the vector is 1. So it's the L2 norm. Thank you. That would have been the shorter answer. Yeah, it's just, whoa, what happened? Yeah, it's just supposed to make this thing 1 so I don't have to write it over and over again. That's all. So I believe for this talk, they'll be finite. So in any given case, if you have an infinite family, that we should be looking at some finite piece of it. Or, you might be looking at like the zeta function or some other L functions in the T aspect, and then you might have a continuous family, but then the measure should be finite. You should be looking at some finite interval. Yeah, so I'll try to give some good examples of the actual families I'm interested in. So the most important foundational example is the classical large sieve inequality for Dirichlet characters. So this is the case where you take all Dirichlet characters, primitive Dirichlet characters mod q or mod little q goes up to capital Q, and then the bound is this completely sharp q squared plus n. No implied constants, no epsilons. It's quite clean. Has important arithmetical applications. So the Bombieri-Vinogradov theorem is one important application. Can get bounds on moments of twists of L functions. And so in the context of the Bombieri-Vinogradov theorem, this tells us something about primes in arithmetic progression, similar in strength to GRH on average. Another thing I wanted to point out, so a large sieve inequality by itself is useless for proving a like a subconvexity bound or just proving cancellation in any given sum. So if you care about one particular choice of coefficients an, and you want to prove cancellation in that one particular vector, the large sieve cannot do that. It's unable to do that because, I mean, you could always choose your vector to correlate with your chi of n's, and then you get no cancellation for that one bad choice of vector. So just because, yeah, so there's no hope in actually using this to prove subconvexity by itself. But I know there are some more advanced applications where you start with some interesting family of L functions, like a moment of that family. You do various transformation steps, and you get to a different family of L functions. And then you want to get a bound on that. And then a large sieve inequality could be very useful for bounding the final stage that then implies subconvexity via the original moment. So that's just a kind of a class of examples. That's one of the reasons why I've become interested in these things. Okay, another example is a theorem of Heath-Brown. So this is a GL1 family. This is more family of Dirichlet characters, but this is a restricted set of characters where these are just the quadratic characters. But the bound here is still q plus n. I guess I probably should say in an upcoming slide that we can never do any better than getting the number of terms on the outside plus the number of terms on the inside as our bound on the norm. And so the previous case, the classical large sieve inequality, you have q squared and n. Those are the number of things on the outside plus the number of things on the inside. And here this has that same feature of size of the family plus number of terms on the inside. This is interesting for understanding quadratic twists of L functions, elliptic curves, and things like that. So passing on to GL2, so there's a theorem of Bézier and Ivanitz from I think around 1978, 79. Where they proved a version, kind of a GL2 version of a spectral large sieve inequality. So this is a case where they have Moss forms of a given level Q, and then you can vary the spectral parameter in some range. And so here, this QT squared is the number of elements in the family. That's the Weil's law, and then plus the n. And then yeah, and here I don't think this is very important for this talk, but there's a weight here that it's natural to put in. That's the reciprocal of residue of the Rankin-Selberg function. Okay, so in all of these cases, I already sort of said this, but here it is on the slide. So in all these cases, the bound took the form elements in the size of the family plus n, and by general principles, you can't ever improve on that kind of thing. Okay, it's pretty easy to prove using duality, and just by sort of choosing one, just choosing your vector an to perfectly correlate with one particular element in your family, like you can't improve on this. So you might start to think that if you pick any reasonable family, that you should get the size of the family plus n. Okay, turns out that's not a good conjecture to make. So in 2007, Ivanitz and Xiaoxing Li studied this family for gamma 1 of Q. So the family of cus forms on gamma 1 of Q. You can take Q to be prime, you can take weight 2 or something like that, so that all of the elements in your family are new forms. So there's sort of nothing, going on with old forms causing a problem. And so the number of elements in the family here is Q squared, and they prove that you don't get this optimistic conjecture of size of the family plus number of terms. So that's the first example that I know about where where the optimistic, I've been calling this the optimistic bound. So if you get the size of the family plus n, it's the optimistic bound. I don't want to make it call it a conjecture or anything, because we shouldn't conjecture something that we know isn't true. But for a given family, you can ask, is the optimistic bound true? Okay. There are more reasons why there are counterexamples, so to speak, to the optimistic bound. So one class of counterexamples was found by Blomer and Buckane. So they studied a spectral problem on SLN with n greater than or equal to 3, and found, so when you study these, like if you use a Kuznetsov formula, like a trace formula, you often will have cus forms and Eisenstein series together. And so that was actually the case with the Désier and Ivanitz bound. I didn't write down what you get from the Eisenstein series, but you get a good amount on the Eisenstein series as well. But here, actually, the Eisenstein part is problematic enough that like you can prove that sort of the contribution of the Eisenstein series alone is not consistent with the optimistic bound. It's just too big all by itself. Okay, so that's what they showed. Okay. Another reason has to do with what I would call having a biased set for your family. So a biased set for your family is a set of integers, let's say between n and 2n, for which if you just sort of sum up your Dirichlet series coefficients along that subsequence, basically there's sort of no cancellation on average. Okay, so this can be like a fairly sparse subsequence, but we're asking for no cancellation along that subsequence. So going back to, as an example of a biased set, if you go back to Heath Brown's result, I didn't really make a point of it at the time, but here it's important, it's absolutely crucial that he has this little star. No one asked about what the star means, so the star should be in square free or primitive characters or some condition that ensures that. So if you like, you could take n and q to both be odd and square free. That would be, that's a good way to think about it. So if he did not impose the condition, the square free condition, on the inside, not on the outside, but just on the inner sum, you could just look at the squares. So if you have a quadratic character, you sum over squares, there's no cancellation along the squares, right? Right. And so you get basically you get a biased set of size the square root of n. And so this is why in Heath Brown's result, he had to assume both the inner and outer sums are square free, we're running over square free integers. So okay, I mean, yeah, so that's another example. I think I have another example coming up in a little bit. What happened with that? Oh yeah, okay. I have another example of a bias set coming up in some slides. Okay. So, and yet another kind of counterexample to the optimistic bound is there's recent work of done in Radziwi about a cubic large sieve. So Heath Brown studied a cubic large sieve, got an upper bound there, kind of using similar techniques as the quadratic case, but he did not obtain the optimistic bound. And then Dunn and Radziwi explained why why he didn't, because there's a main term there. Like yeah. So basically, Heath Brown's result was optimal. So yeah, so this, I mean, for me, this makes life kind of exciting. We don't really know. If you've got a family, you don't know what the truth is, you know, and so okay, so that I think that's part of what makes it fun to work in this area is trying to figure out what's going on. So, and then in any given family, then you don't really know. You have to work on it to try to get a better feel on what the truth actually is. So the main family I want to talk about today is a family of Eisenstein series with on GL2 of varying levels. So so if you take a pair of Dirichlet characters, in this case, I actually want them to be the same. In this case, this is a chi, and then the other one is conjugated. But in general, if you have a pair of Dirichlet characters, there's say a primitive Dirichlet characters, there's a new form Eisenstein series attached to that pair of characters. And if you want to have a new form Eisenstein series that has trivial central character or trivial Nebentibus character, those only occur when the level is a square. So capital Q is little q squared, where the two characters are mod q. And then the two characters are also equal. And so then the Dirichlet series coefficients of these Eisenstein series are given by this kind of divisor type function. Okay, so that's a classification of the new form Eisenstein series. So if you want to study a large sieve inequality for these things, we should study them for new forms, because that's the analog of primitive characters. So maybe I should have said, so going back even to like the classical large sieve inequality, where we had all primitive characters mod q and little q up to capital Q, and that setup, if you don't assume the characters are primitive, if you just try to take all characters, you don't get the optimistic bound, basically because the trivial character appears over and over and over again. There's this massive repetition. So you always want to make sure that you don't have the same element in your family counted with too much multiplicity. So that's the analog here. We want new forms. Okay, so basically, yeah, these are the Dirichlet series coefficients that I'm interested in. So if you're not a huge, Eisenstein series person, this is really just, you could just think about Dirichlet characters and look at these divisor sort of convolutions as the coefficients. Okay, so let's define the norm for this family to be the following. So we've got, the usual thing on the inside now. We've got our arbitrary vector, we've got our coefficients. I'm plugging in 0 here. I guess I didn't say much about it on the previous slide. Where did it go? Yeah, so you can also put in this a over b to the IT. I mean, if you're more used to like the level 1 Eisenstein series, that's like the case where the characters are trivial, and then this is maybe what what you might be more used to for the usual Eisenstein series on SL2Z. Anyway, so I want to focus on the level aspect. So let's just take t equals 0 and not worry about it. We could take care of the t aspect as well. Okay, so then on the outer sum, we've got all Dirichlet characters mod little q and then all little q. So this looks a lot like the classical large sieve inequality. In fact, you can use the large sieve inequality to give you sort of a warm-up bound. So the warm-up bound you get is q squared times square root of n, and then there's an extra n log n. Maybe the easiest way to see this is to use duality. And then, so n is like you have a double sum over a and b, and then it's really like Dirichlet's hyperbola method. So one of the a or b you just don't do anything with, and maybe you take the smaller one, so that goes up to root n, and then the other one you apply the usual large sieve on. Okay, so that's a warm up. Yeah, okay, so I wrote it on the slide, use duality and this hyperbola method. But it turns out this is actually best possible. So there's a biased set coming from prime squares. So just like for in the Heath-Brown quadratic large sieve case where the squares are a problem, the squares are a problem here as well. So we have a very simple formula for lambda of p squared. It's 1 plus chi squared of p plus chi bar squared of p. And basically, if you sum this up over p, the chi squared of p and the chi bar squared of p cancel out, except in the very rare case that chi is quadratic, but those are so sparse that they don't matter. So basically, you see this bias with the +1. Okay, and so yeah, so this is a biased set in this family. Okay, and so that means, yeah, and so that implication is that we can't ever beat this q squared times the square root of n bound. Okay, so we could sort of do the same thing that Heath-Brown did and just put on some extra condition that avoids this problem. So what I did here is I put on this little condition that the GCD of A and B is equal to 1. So that avoids the A equals B equals a prime situation. And so at the very least, this avoids the sort of known counterexample. Okay. And then it turns out that if you put on that condition, now you can get the sharp large sieve inequality of the size of the family plus n, although with an extra, everything is to the, you've got this epsilon here, and the implied constant depends on epsilon. But okay, so that's the main result that I want to talk about today. So I also would like to, before I go off and say anything about the proof, I'd like to just completely reinterpret this result in a way that, I don't know, I'm kind of curious if how natural people think this looks. But okay, here we go. So there's a way to think about all this in terms of sort of sieving rational numbers rather than sieving integers. So okay, so I don't like the notation that I'm using here, this q sub q. It's not the p-adics. So you take the rational numbers and then you take rational numbers whose denominator is coprime to q. Okay, that's what the set is. So this is a ring. Okay, and then if you have a rational number and the denominator is coprime to q, then you have a reduction map mod q, and that's a ring homomorphism. And if you have a Dirichlet character mod q, you can define chi of one of these rational numbers just by taking the reduction. Okay, so in particular, so if your rational number is a over b, then this is just chi of a times b inverse, the b bar. Okay, so that which is the same as chi of a, chi bar of b, and that's the exact same thing that was in the definition of the coefficients of the Eisenstein series. Another thing, so I'd like to define the height. I don't know, people might not approve of the word height here, but it's just the height of the rational number for this talk is just the absolute value of a times b when a and b are in lowest terms. Okay, so that's just the way that they're ordered. So if you do that, then with that definition, then we have a large sieve inequality for these rational numbers. So you take any vector alpha indexed by these rational numbers, and you take chi evaluated at these rational numbers, and you order them by the height there, then we get this kind of sharp large sieve inequality. So, and there's no content to this beyond the previous theorem. This is just a pure reinterpretation of the previous theorem in this language. So, so that's my proof for, they say you should have at least one proof in your talk. I don't know if I really agree with that, but anyway, there's zero content to the proof. So, so as an application, I came up with a kind of a sieving application. So one of the historically, the classical large sieve is, I mean, the way I stated it has really nothing to do with sieves, but it has been used as an input in this sieving problem. And you can do the same thing in sieve rational numbers. So that's what this slide is explaining. If you're familiar with the classical large sieve, this is almost the classical version of the arithmetic large sieve. Then this is basically the same thing. So you just take your rational numbers ordered by height. You take some finite set of primes. For each prime in your set, you pick a subset of Z mod P. That's what this omega P is. And then define this function, omega of P, that's cardinality, and H of P is this ratio, omega of P over P minus omega of P, extended to square freeze. So, okay, so I'm going through this quickly because if you've seen this before, then you just know it's the same thing. And then if you haven't seen it before, then this doesn't really come up in the rest of the talk, so maybe it's okay. But anyway, yeah, so and maybe the best place to look is just about the classical version. But anyway, so now define this set S of n p omega. So those are the elements that remain in your set after throwing away all elements that land in omega p for some p. So you throw that set away, and then what's the set that's left? Well, the arithmetical large sieve gives you an upper bound on that set. And it's this n plus q squared. So there's, compared to the classical large sieve, it's not quite as nice because we've got this 1 plus epsilon. But the denominator is still this thing h. So yeah, so in order to get something interesting, you want this to be strictly less than n, right? N is the trivial upper bound here, or I guess the cardinality of the set, yeah, which is around n, or n log n. So yeah, so you need h to be growing at least like n to the epsilon in order to get something non-trivial out of this. So you need you need to be sieving out enough enough large moduli that something happens. But yeah, so like the most basic case to think about is just imagine taking just half of your elements mod p and just throwing them away. So for every p, just randomly pick half of your congruence classes mod p, and then throw away any rational number that when you reduce it mod p lands in that set, then the cardinality of the set that's left over is basically square root of n, or n to the half plus epsilon. Yeah, it's not, you don't get anything very interesting by looking at squares, I think, like, but anyway, maybe I should just not say anything about that. Oh yeah, okay, so I made a slide on what I just said. So the classical case is you just throw away half the elements mod p. Okay, so the proof is much longer and more involved than for the classical large sieve. And so there's three main tools that go into it. So the first one of these three main tools is a monotonicity property. So that's the following. So if you can, that's what I mean by this monotonicity. So if you take, let's say a q prime just a little bit bigger than q, maybe by a factor of a log, then the norm only increases. And then the same thing is true in the n aspect. What did I? Yes. Yeah, that should be an n. That's a typo. Yeah. Okay, people are awake. Good, good. Okay. So the idea for the monotonicity is similar to an idea from 1973 of a paper of Forti and Viola. And so it's a beautiful idea. And so what you do is you just add a new prime, or new family of primes. And just, so this first line here, I've just done absolutely nothing. I've just added a sum over primes and then divided by, so P star here represents the number of primes. So I've done absolutely nothing on the first line. Now the idea is, well, just put in absolute value of chi of P squared, which if you put it inside the sum is a chi of P. The only slight lie here is, well, what happens if chi of p is 0, then you might have made it a little bit smaller. So you have to sort of take that into account. So that's why this is a squiggly approximation sign. So in practice, you have to actually say, well, if p divides q, then one thing happens, but it's not too bad. And yeah, and so then once you've got this p on the inside, then what you do is you say, okay, well, let's let a times p be a new variable that is now sparsely supported. It's supported only on the multiples of p, but if a had length n, or a times b had length n, then now the new sum has length n times p, so it's longer. And then this is just an average, so you can just sort of take the worst case and like max over all the primes, and then the norm just gets increased in this way. And then there's kind of a similar argument for monotonicity in the Q aspect. And for me, it's most convenient to see that using duality and kind of doing similar tricks. Okay, so it's a pretty, this part's pretty easy. So in terms of, yeah, pretty elementary and kind of nice that it's not too difficult. So the next thing is to use a functional equation. So this is a pretty common technique when studying these kinds of bilinear forms, that you can always take the sum over n to the outside and square it out and apply a functional equation of a Rankin-Selberg-L function. Sometimes this is useful, sometimes it's not, it sort of depends. Here, let's just see what happens. So I've got some text in red to represent that it's a problem. Okay, so here's the sum. So this is what you get if you use duality and take the sum over n, or in this case a and b, on the outside, and then the family is on the inside. Okay, and then you have a different vector. This is just your arbitrary coefficients, let's say beta chi. So if you just square it out, that just means repeating the sum twice. You get this sum. The characters kind of get arranged in this interesting way, like chi1, chi2 bar of A, chi1 bar, chi2 of B. Now, the problem is that this GCD condition, so if you convert to, take the Dirichlet series associated to this sum, you get the L function, chi1, chi2 bar, and then chi2, chi1 bar, but then this gives you a zeta of 2s. And that's a problem, because if you want to use a functional equation, basically you want to shift contours and all this stuff, and the zeta of 2s downstairs prevents you from doing that. Even if you assume the Riemann hypothesis, that still prevents you from, that would let you move to like a quarter plus epsilon, but you couldn't move past that. You'd hit all these poles and it'd just be a huge problem. Okay, so this GCD condition, on the one hand, is absolutely necessary to have it there, but it's also a big problem, right? Remember, the original definition of the norm did not have the GCD condition, but then I showed you there was a biased set, and so we couldn't get a good bound that way. So we're kind of, in a difficult spot. Yeah, okay, so this is just what I said. So here's a compromise. So instead of completely dealing with this GCD condition, let's use some positivity and so, it's a compromise. Okay, so I don't know if you can read it. This is orange, like an orange traffic light. This is no go. This is maybe, I don't know. So yeah, okay, so how to read this? So if A and B are relatively prime, then this denominator is 1, and I want to choose y a little bit smaller than n, so that if, from the terms where A and B, the GCD of A and B are 1, then they're still included here. So this is just only including possibly more terms, and obviously everything is non-negative, so we can do this. Yeah, so I guess you could rearrange this. So the GCD of A and B squared is less than n over y. And so the bigger y is, the smaller the GCD is. So the bigger y you take, the smaller the GCD is. So you're allowing the GCD to have some size, but hopefully not too big. So it's a way of controlling that GCD. So this kind of idea was used by Heath Brown in his quadratic large sieve. He had this square free condition that on the one hand he needed, but it was a problem. I mean, the issue is, the Poisson summation or the functional equation for Dirichlet functions doesn't hold for square frees. You would kind of have to sieve, and it's sort of fundamentally the same sort of problem here. Okay, so now what we'll do is use inclusion exclusion. So this condition that this condition now gets sort of flipped. So this condition was saying that that it's bigger than y. So then what we'll do is say, well, let's extend this to all a and b and then subtract off where it's smaller than y. Okay, that's the idea. That's what this notation is. So S infinity means no condition on a and b. The S less than or equal to y means we've truncated it at y. Okay, and then we're going to use different techniques for the two pieces. So for the part where it's truncated at y, this is the easier piece. The idea here is, well, basically you can sort of factor out the GCD here, like replace a by sort of, you know what I mean? Like just substitute or multiply a and b by their GCD. That will cancel this here, and then the new a and b are relatively prime. And then so the sort of the GCD variable is then sort of free, except you see it in here. But it basically does nothing here. I mean, there's a little coprimality condition that I want to ignore, but that basically forms a zeta function. That's where this zeta of 2s comes from. And then what's left over, you still have the GCD as 1, and then you truncate it at y now. So now you've shortened that sum. Okay. So yeah, so that's good. So we've chopped it off at y, but we've made a new zeta. Okay, and so now the idea is let's shift contours to the left. That should be the right direction to go in, because we want n to the s to be small in absolute value. Now, yeah, so you can see if you shift contours, we're going to hit a pole of this zeta function, and that's going to give a term. So that's sort of the bad news, if you like. So there's a pole at s equals a half, and if you just sort of write it down, you get a square root of n here, square root of ab there. There's this Mellin transform, whatever it is. But now so you just get this term. It's a polar term, and there's basically nothing you can do with it. You just have to just leave it alone. You can't bound this in an acceptable way by itself. So even if you assume the optimistic bound for this large sieve, so if you're willing to just plug in a good sharp upper bound on this sort of causes problems when a and b are small. You've got this huge square root of n there. So you can't do anything with it all by itself. Okay, so that's the bad news. So the good news is on the new line of integration, everything is good. You've got basically you're back to where you started from. You've got like it's like a new instance of your problem that you started with, but the length of summation, your n variable is now chopped off at y. It's much smaller than before. So you've got a gain from that. Okay, so that's this part. And then there's the S infinity part. That's where you've got no condition on A and B. So that's I don't know if it's very legible, but this is green. This is full speed ahead. So it's this funny paradoxical thing. Like you don't want the condition, but you need. You need the condition that GCD of A and B is 1, but you don't want it. It makes it difficult. So that's kind of the whole game here. Anyway, so if you just square this thing out, you get this. You get your betas twice. You've got your family twice, and then take the Mellin transform. So you get your n to the s, w tilde of s, and your product of your two L functions. Okay, so now there's a technical problem that I don't want to get into the mud in here in this talk, but there's all sorts of issues because chi1 and chi2 are primitive, but the product of chi1 and chi2 bar does not have to be primitive, and there's many ways that this can sort of fail. They could have, on the one hand, they could have completely coprime moduli, and then it's really primitive, and that's nice. They could have equal conductors but still be primitive. They could have equal conductors and be equal, and then the conductor of the product is 1. And so you've got all this variation in what can happen. But okay, so for this talk, let's just look at the 2 most extreme cases. So that's like the diagonal case where chi1 equals chi2, and then there's like the completely sort of orthogonal case where the moduli are relatively prime altogether. So the diagonal is easy. That's basically, this is like zeta, this is a zeta, and you just get like you get a pole at 1, it's a double pole, but you get basically like an n log n. That's a diagonal term. That's expected that we should get something like that. Okay, this should probably be a log n, but n to the epsilons and such I'm ignoring in my slides. Okay, so I don't want your eyes to bleed staring at this, but let me just say what's going on in this slide. So you want to apply the functional equation. It's basically you want to use like Poisson summation for your family. So you go to L functions, shift contours over, apply the functional equation, change variables back, and that's what this is. Okay, so one of the nice features about this family, so you've got chi1, chi2 bar here, chi2, chi1 bar here. When you apply the functional equation, it conjugates this character here, and it conjugates this character there, but those basically just interchange the 2. So the product of these L functions is self-dual. So that's sort of the reason why, I mean, it's no accident. This came because the Eisenstein series have trivial central character. This thing down here is the conductor of chi1, well, it's really the conductor of this product of these 2 L functions, which is this q1 squared, q2 squared, in the case that they're relatively prime. Okay, so now basically, now that we've done this, you can chop the new sum off. The usual way you do this is you say, well, this is harmonic analysis. The product of the original length and the dual length is the conductor. So in this case, the conductor is like q to the 4th. So the reason it's q to the 4th, if you're wondering q to the 4th, well, this has conductor around q squared because we're assuming that these have relatively prime moduli, and this one also has q squared, so in total q to the 4th. So, okay, so this functional equation side of things should only really be good if n is bigger than q squared. If n is smaller than q squared, the length of summation is longer than before, and this shouldn't be very helpful. But if n is larger than q squared, then this functional equation step should be giving us good information. Okay, so we need to circle back to where we started from. And so for that, we need to pull out the GCD of A and B. So factoring out the GCD of A and B, like maybe going back one slide, all that does, so in here, if you factor out the GCD of A and B, that's just going to give you a zeta of 2s. Because again, the GCD here, you sort of don't see it with the characters, like they cancel out. So you get another zeta of 2s. This is actually good. If you thought the previous one was bad, well, once you've got it, you need another one because the actual will have to cancel. So you get another zeta of 2s. Now we're going to do the same thing as before with the truncated part. Shift contours back. You hit a pole at a half again from that zeta. And then amazingly, these 2 terms, the 2 polar terms exactly cancel if you choose your value of y the right way. So if you choose y to be this truncation point, you can just see like they just exactly cancel. So in a way, it feels like a miracle that the 2 things cancel each other. And then on the new line 0, you get you get this thing. So you've got an n from up here. This is basically q squared because it's q to the 4th square rooted. The family stayed the same, so that's your family parameter. And then the new length of summation is q to the 4th over n. Okay, so so in summary, this functional equation result is giving you a relation that the norm satisfies, a relation sort of between itself. So it's not, it's like a relative formula. It tells you something about delta of qn in terms of other delta of q n's for other value of n. Okay, so that's I mean, maybe the hard the hard part. Now there is okay, so this is the second main tool. So the first tool is monotonicity. This is the second tool. There's one more tool, which is very much analogous to this functional equation tool, but every single step is different. So this third one, I would call it like maybe the family sum result. So for the family sum result, you study the problem from the dual side. So you've got the family on the outside and on the inside. And you get a very much similar kind of structural type result. In the end, you get another self-referential result. So that probably sort of skim through the proof here, but clearly this looks a lot the same as this other one. Just sort of change n and q squared around, sort of squint at it. They basically are the same sort of result. So now it's kind of a fun exercise to derive the main theorem, the upper bound on the norm using these three things. This is basically something like Heath Brown did in his quadratic large sieve paper. It's just like a fun exercise. So if you're willing to grant these three results, it's pretty easy to prove it. The idea is you sort of start with some sort of crude bound, like maybe whatever trivial bound you have, and then you sort of follow, you probably have to use some monotonicity, sort of chain these things together, and then you get the same sort of bound, but with better exponents. And then in the limit, the exponents become optimal. It's kind of amazing, at least to me, but that's the overall structure of the proof. I mean, another thing, like just, I guess, maybe to say in the context of this conference is that there's this really, pervasive thing that, a lot of times you have this orthogonality formula for your family that you want to work with, well, okay, I guess maybe so maybe I should say so far in the slides I've talked about, like there's that condition that the GCD of A and B is 1. You don't want that. You want sort of all A and B, but the GCD being 1 is sort of forced on you to get a nice result in the end. This is kind of analogous to sort of working with all Dirichlet characters versus primitive characters. So maybe I should explain that better. Maybe that's better explained in the next few slides. So, but yeah, okay. So let me just, maybe I'll come back to that thought. So if you study this problem on this dual side, that's where we've got this sum over characters on the outside, and then this thing on the inside, the GCD equals 1 condition. I've put in red this condition that chi is primitive. This is necessary because otherwise you get the same thing repeated over and over again, and you're not going to get a good result. But so let's just leave it in there and see what happens. If you do that, there is an orthogonality formula for primitive characters that you just get by inclusion, exclusion, or sieving. And that leads to this Mobius function here. And then when you go to Mellin transforms and everything else, that Mobius function causes you to have a zeta downstairs. And that is like very much analogous to that zeta of 2s that was downstairs that came from the GCD equals 1 condition. And this prevents you from shifting contours and doing all analysis you'd like to do on this problem. So this is what I was trying to get at, was like, in practice, we like to work with all characters, but we're sort of forced to work with primitive characters. And this is something we see with moments and other things. Anyway, so that's just I don't know, I was trying to shoehorn a little bit of this into the topic of the conference with random matrix theory and families and orthogonality, etc. Okay, so now I very much want to follow the same sort of style as before. So I've got this condition that is primitive. That's hard to deal with, but we need it. So let's compromise. So let's compromise by saying, well, let's take characters with sufficiently large conductor. Let's say at least some parameter y that we choose later. As long as y is a little bit smaller than q, then we get everything that's primitive, but we also get some more. Okay, and now we'll do the exact same thing, sort of inclusion, exclusion, sort of overextend to all characters, and then subtract off the ones with conductor at most y. for the conductors at most y part, you sort of do the same thing where you sort of go back to your starting point just by combinatorial type reasoning. So yeah, so if you have all character, like, if you have characters and they're conductors at most y, you can just sort of factor your character as something trivial times something primitive. And then the trivial part will give you a zeta is basically what's going to happen. That's this zeta. And then what's left over, you've got it chopped off at y. So again, you want to shift contours over to the left. This zeta gives us a pole. This time it's at 1, but yeah, that's no big, that's not a huge difference. And so you get again, you get a polar term here. But on the new line, you get something good. It's like I'm trying to draw your analogy. I know there's a lot on the slides, but so here you've got, now it's very much like before where we've got this, it's like a new instance of the same problem, but with smaller parameters. And then for this extended part where we have everything, this is now in green because this is all characters mod q. This is the family that's in practice easier to work with. But secretly we know it's going to cause some issues that we have to overcome. So if you just square this out or square this out and apply orthogonality of characters, you get a congruence. So in this case, the congruence will be sort of a determinant type equation. You get a1b2 minus a2b1 is divisible by q. These things are relatively prime. That will be important. W1 is basically, I think that's just little q or little x times w of x. So it's like anyway, it's just a slightly different smooth function related to little w. So here you get a diagonal. So when a1b2 is a2b1, you get a diagonal term. You get this for every single value of q. And here is where you actually see that this GCD condition is crucial. Here, this forces, since A1 and B1 are relatively prime, this one, and same with the A2 and B2, that forces A1 to equal A2 and B1 to equal B2. And so it really collapses to the true diagonal say on the rational numbers. So, okay, so that's like that diagonal term. For the off diagonal terms, I want to use a method or trick, if you like, this divisor switching method that I was inspired by in Connery and Ivanitz and Sundararajan's paper on the asymptotic large sieve. So they use this, they were studying like an asymptotic version of this, but for particular choices of vectors. And it wasn't this particular, this chi of A, chi bar of B, but anyway, they still end up with a congruence, and they use this divisor switching trick as a crucial step in their work. So the idea is, so you've got A1, B2 minus A2, B1, you write that as Q times R, and R is your new parameter. So it's like you want to eliminate Q and substitute that everywhere, and R is your new modulus. Basically, R goes up to N, like if this goes up to N and this goes up to N, then R is going to go up to N over Q. So now if, let's see, if N is smaller than Q squared, this is now smaller than before. And R is smaller than Q then. So this is exactly like the complementary range to the functional equation side of things. This is beneficial in the completely complementary set, but relating N in the size of N and the size of Q. And so I would say that this basically this divisor switching trick is the same as analogous, very much analogous to the functional equation of the L functions on the other side. So you might think of this as a functional equation. I don't know how much of a stretch that is, but I think, yeah, there's words you can say. I think it is very much a functional equation. Okay, so so basically you just do that, you plug it in, you're going to get another, okay, I kind of want to skip through the technical details, let you all drink some wine. So so once you've got that idea in mind, it all sort of comes together, you get some sort of variant on your original sum. This is a zeta that comes from the same source as like going back to primitive characters. Yeah, and so in this great big expression, you shift contours back. This time you hit a pole at 0, but like back in terms of the original variable, that's like 1. So again, you have to shift contours to get another pole, and it exactly cancels the first pole. Okay, from the the s less than or equal to y polar part. I should say like this cancellation of poles happened in Heath Brown's paper on the quadratic large sieve. That was crucial there, and I was inspired by that for this. But yeah, and so the poles cancel if you choose y appropriately, and then on the new line you get a new version of your original problem. That's it. I'll stop here and let you go get some wine.
Yes. Part 2 and part 3.
Part 2 and part 3.
Your main theorems for the functional equation at the condition n will be less than square in the part 2.
In part 2. So there was so so you want the functional equation theorem? This one? This is the second main thing.
These contradictory, you want n to be very larger than q squared.
Yeah, you want n to be larger than q squared for this to be good. Like you're not going to get much out of this if n is smaller than q squared. But then the other result, this family sum one, it should go the other way. So you just chain them together. So it's like you start with some range of parameters. Often you actually have to use monotonicity. You choose sort of extend one of your parameters the right way. Apply the functional equation that gets you to some new land, but you're in the flipped situation now. And then apply you might use monotonicity again, but then you chain the two things together. So you do one full cycle with the two results and you're back, and you get a better bound than what you started with. It's kind of a fun exercise, actually. You could just sort of do it. Like it could be like a contest problem for high school students. Like it's really just algebra and like kind of a fun recursion.
The second result is being used implicitly in this third.
In the what result?
The third dual set.
This one right here?
Yeah.
This is completely independent of the second one.
Equals 1.
Yeah. Yeah. That's baked into the GCD equals 1 is baked into the definition of this delta.
Okay, Enrich, you have to combine it with the first principle that you established, right?
Well, the duality principle. Yes, yeah, that's yeah. Yeah. So you're saying I have to use duality, yes.
One step.
Was I mean
Very careful because you can set it up this way. It doesn't matter, it's the same thing.
We can talk, yeah, I mean, yeah, you have, but yeah, so like, I guess one thing was, yeah, I'm not exactly sure I understand here. Maybe we could talk about it.
Not to that.
Question.
Forgive me if you mentioned this already. The n to the epsilon and q to the epsilon factor that you have in your upper bound, is that necessary? Does that have to be there?
The way that I've proved it is necessary. Yeah, you could speculate about trying to get rid of those. I mean, one thing I lied. So in these statements I lied. There should be epsilons everywhere. So as soon as you have one epsilon, it kind of infects everything. So you might be able to work a lot harder and get some logs. But it's kind of tricky because you iterate this. So if you get sort of a multiplicative log, then each time you iterate, like that gets multiplied, and people worry about how much it explodes when you do that.
Do these just come from every time you're applying the monotonicity principle, you're using a log, or are there other places where
you don't lose a log in monotonicity. I mean, you just need to make sure you're a little bit far enough out that the monotonicity, like you have an absolute constant. There's no log. It's just you need to at least log times farther out in order to apply it. But in all these results, there's some I don't know. I would be, I don't know. Maybe you get some gigantic power of log or something. I don't know.
It's the same thing in Heath Brown's paper, right?
Yeah, it's exactly the same situation. Yeah, it'd probably be easier to try to get rid of the log in his paper.
So I think like 7 years, I sketched something out, and I think you get something like expo log over log log. I think it's like quite bad. It's like quality of the divisor function. But, like,
So I've ever,
but I never.
if not everybody heard Ian, he said that you might be able to do it, but you get some horrible bound, or, I mean, it's not, maybe extra log or log log.
Yeah.
Okay. Do you have any applications?
So I tried to sketch those I'm interested if there are applications, but I think, yeah, I don't know. Are people interested in sieving rationals? If you are, then this is useful, I guess. So I don't know. I didn't have any.
If you want to see rationals, what happens if you try to use the additive?
Well, just.
It's because your height is multiplicative, I guess.
Yeah, so, I mean, you can prove, yeah, this, I don't know how to prove anything about anything. Yeah, I don't know. I don't think the additive version helps. I mean, it's sort of the same. You can prove the additive version from this, from the multiplicative version for rationals.
You might be interested in the usual height, so maximum of A and B instead of.
Yeah, you could do that. Yeah, no, this is like a hyperbolic.
You have no automorphic application in mind?
I have for generalizations of this, I have some applications, but that's work in progress with Ian. So maybe I'll be able to report on that. Too long.
The 75th birthday month.
Yeah, we'll see. No
Any
problem.
further question? Or do people just want to have wine? Is the wine there?
I saw him saying, yeah, I see mine.
Okay, well, then let's thank Matthew.